Welcome to Math 119, Chapter 5.5, where we talk about graphing rational functions. So a rational function is a function of the form p of x over q of x, what you see down below, where p of x and q of x are polynomials. So you assume that p and q have no factors in common while it's in this form. Even though all rational functions are constructed from polynomials, their graphs are going to look quite different from the graphs of a polynomial. Now, keep in mind, polynomials take on the form of x squared, x cubed, x to the fourth, and so on. But the more that complicated they become, right, the more complicated their graph looks. So perhaps we have a concave up graph. Sometimes we have, well, this is an S-shaped curve, right? This one could have lots of bumps. And again, this one could have a little bit more waves. It all depends on your terms that are in your polynomial. However, for us, our rational functions will not take on this specific look. Instead, they're going to look a little bit more complicated. So it says the domain of rational function consists of all real numbers except those for which the denominator is 0. Excuse me. That's just another way to say that because with your denominator, right, we don't want to divide by 0, right? We don't want 0 in the denominator. We want to find, well, what would that be, right? So when it's in this form, you'll notice that it's hard to pick it out when it's in this expanded form. So instead, we would need to factor. So we're looking at factors of 12. So 1 and 12, 2 and 6, 3 and 4. That can get us to a positive 7. Well, that's 3 and 4. And they both have to be positive to make positive 7. And when multiplied together, they'll make that positive 12. So these are just going to be your factors. So we have x minus 1 over x plus 3 and x plus 4. So we can see in this form what your zeros could end up becoming, right? So if we take out x plus 3 and set it equal to 0 and x plus 4 and set it equal to 0, x is equal to -4 and x is equal to -3. Do we want -3 and -4 to happen? No, right? Because if we plug in a -3 here, we're going to get 0 multiplied by a value. So again, 0, which you'll have a 0 in the denominator. Same thing if you were to plug in -4. So these are going to cause vertical asymptotes. These are numbers that we want to avoid. So we have to pay special attention to your end behavior at these particular values because, again, these are your asymptotes. So if we put this onto a really quick number line, -3 and, -4 and -3, you can be any number for x. You can plug in any number for x except for -4 and 3. So for your domain, we have -∞ to -4, union -4 to -3, union -3 to infinity. Now what happens at these values is your graph is going to kind of skyrocket up or down at these values. And to determine that, we just have to start learning some of your graphs. So the values of your denominators, as we just discussed, will result in vertical asymptotes. So take, for example, f of x is equal to 1 over x. Now back from when we were talking about transformation of graphs and your other graphs section 3.4, we talked all about what this particular graph should look like. Right? We talked about some patterns. So this one should look like the one where it diverges. Now I want a better picture than just a very simple one. So let's go ahead and plug in some x values. So on this side, because my x's are positive on this side, I'm going to plug in some positive x values. And I'm going to do the same over on the left-hand side, except for positive, I'm going to do more negative numbers. Let's see if I can do that again. There we go. So what are some positive x values that we could plug in? Well, you could plug in 1, you could plug in 2, you could plug in 3, right? But what about some smaller numbers as well? Could we plug in, let's see, 1/2 or 1/3? And notice, what number am I going to have to avoid? We're going to have to avoid, when x is in the denominator, we can't be equal to 0. And again, we just talked about this being a vertical asymptote. So where on your graph is x equal to 0? Well, that would be on your y-axis right here when x is equal to 0. So we can choose any positive number, and we just cannot choose x being 0. So for when we go to choose, we have 1 over 3, right? This one coming from up here, and then your 1/3 that we may have picked, right? We're going to keep change flip. So 1 times 3 over 1 is now 3. So we have the point 1/3 and 3. And if we were to do it again with 1/2, we have 1 times 2 over 1 to make 2. So 1/2 and 2. 1 over 1 is just 1. So the 0.11 is nice. And then 1 over 2. So you have 2.5. We have 1 over 3 for 3.5. So on the right-hand side of your graph, we should have, and if I were to make a really quick notation, we'll say this is 1, this is 2, this is 3. So we have, let's see, 1, 1, 1. We'll just go up. I have, so let's say this one is 1, 2, 3. So 1 is right here. We have 2.5. We have 3 1/3. And then we have 1/2 and all the way up at 2. And 1/3 at 3. So somewhere up here. So then what does it look like your graph is doing? Well, it looks like we're going to come all the way from a very high position. And we're going to scoot down low. Now let's have you try it again, but for your negative sides. So again, what we just did when we had x is greater than 0. So let's do it when x is less than 0. So some negative values. So we can choose the exact same ones, but maybe their negative counterparts. So negative 1/3, negative 1/2, negative 1, negative 2, and negative 3. So you have negative 1 and 1/3, negative 1 times 3 over 1. Sorry, these are both negative values. Negative 1 over 1. Negative 1 over 2. So we're going to be in the third quadrant where both of your values are negative. So again, if I were to give a little bit more context, we've got negative 1, negative 2, negative 3, 1, 2, 3. We should have the same idea here. So we have negative 1, 1 right here. We have 1/2 and negative 2. Third. Let's see, 2.5. Third. So again, what does this one look like it's doing? looks like it's going to start to approach your vertical asymptote. So it'll go down like this. Now, what do you think is happening at this particular value when y is equal to 0? What could it look like? Well, if we wanted to, we could choose more fractions and get as close as we can to y is equal to 0, right? But look how it's starting to flatten off a bit, right? Just like it's flattening off and going super high, like going really, really quick as we get to your vertical asymptote. Same idea is if we have a horizontal asymptote, where we have y is equal to 0. Now we're going to learn why that one is, how to get horizontal asymptotes. But for your vertical asymptotes, we're primarily looking at your denominator. So let's round that home for here. These, again, dotted blue lines are suggesting, just like as we had over here, that we have some asymptotes. So can you pick out your asymptotes? Where are they occurring? Now, hopefully you're not saying, okay, this is just at 1 and 3. Well, you're right. These are values of 1 and 3. You have a vertical asymptote at 1 and a vertical asymptote at 3, but it's not just at a specific point. Instead, it is actually a line. So we actually have to say x is equal to 1 and x is equal to 3. It's a whole line that your graph is trying to avoid. Now, vertical asymptotes we can never cross. Now, do we have a horizontal asymptote? So we do have a horizontal asymptote, that being this horizontal line. And where does this line occur? Well, this is when y is equal to 0. Now, does it appear that we can cross a horizontal asymptote? So unlike vertical asymptotes where we cannot cross them, horizontal asymptotes, we can at times cross them. Because you'll notice right here that we're crossing at x is equal to 2, right? So horizontal asymptotes can cross when between two vertical asymptotes, or when x is not going to infinities. It doesn't mean that they're always going to cross between these two asymptotes. It just is suggesting that they could cross at times. And the only way we can figure out if they cross or not, this one is crossing at your x-intercept, but is to actually pick points and start to graph, get a good idea for what they look like. Now, we're not quite there yet, but we will be. When we talk about finding, we want to start to actually find some of your elements first before we can actually get to that point. So first up is to find your vertical asymptotes. So your vertical asymptotes, step 1 is to factor. So step 1, factor your denominator. Even if you have your numerator, you would want to factor your numerator as well. But if we're talking about vertical asymptotes, that's what we want to look at first. Then set your factors equal to 0 and solve. The vertical asymptotes is a line, x is equal to a, for the values that result in step 2 from above. So let's take a look. If you want to pause the video, I would suggest it if you want to get a head start. Otherwise, I would pause the video after A. But take a look at A. If we have already had it in your factored form, right? This one being, it's not factorable, it's already in its form, right? It's not a trinomial that we have to work with. Instead, again, we're trying to figure out what number do we want to avoid. So we set x plus 2 equal to 0. Subtract the 2 to the other side. Now, do we want x to be equal to -2? Now, this is a value that we want to avoid, right? In your denominator, not your well, yes, in your denominator, we want to avoid this number. But on your number line, we don't want -2 to occur. So in your domain, we have to avoid your -2. So for your domain, we'd be going from -infinity to -2, union -2 to infinity. So if we're being asked, hey, what is the vertical asymptote? Well, your vertical asymptote being a line, we have x is equal to -2 here. This is the value to avoid. There is a void in your graph that we have to jump over. So let's try it again over here. And again, look to your numerator as well to see if it can factor, because we're going to be talking about wholes here in a minute. But since the numerator is not going to factor, we're going to look at your denominator, and we want to factor your denominator. So you have x squared plus 1 over x minus 3 and x plus 5. So since nothing is going to cancel, which we'll talk about here in a moment what we do when we cancel, right? But we have values to avoid. Again, we don't want your domain, your denominator, to be at your factor. So we can set x minus 3 equal to 0 and x plus 5 equal to 0. So x is equal to 3 and x is equal to -5. These are your vertical asymptotes. And again, these are numbers that you don't want to be in your domain. So we would want to skip these values. So we got -5, we have 3. So we're going to be jumping over these values in your domain. So we're going from -infinity to -5, union -5 to 3, union 3 to infinity. Again, we're trying to avoid your vertical asymptotes. We're going to see some strange behavior happening for your graph. So let's try C. So while it appears, right, that we have a vertical asymptote at x is equal to 1, let's pause for a moment and see, can you also factor your numerator? Well, your numerator here is x plus 1 and x minus 1. And you have an x minus 1 down below. So what is going to happen next? Well, because these cancel, what have you made because you've canceled it? Well, you've made a hole in your graph. And where does this hole occur? Well, if we use the same idea as before, right? If there's a hole in a graph, like if there's a pothole on your highway or on your drive, right? You want to avoid it. You're going to go around it. Or maybe you go a little bit slower if you can't swerve, right? But you're going to avoid 1. So there's a hole when x is equal to 1. And again, this is a value that we don't want to happen. So for your domain here, we're going to go from -infinity to 1, union 1 to infinity. And again, your simplified version is just x plus 1, which if I said, hey, could you graph this? Right, well, we certainly could graph it. This is just a line with a hole at x minus 1. So notice that at your point 1, 2, right, it says undefined. What they should do in Desmos is actually show you that there is, notice how there's that now white hole, if I can get it to stick, right? There's that white little hole that suggests that you have to actually jump over your value, right? That is just like here. Now to find the point of your hole, well, you have an x value, we can go ahead and plug it in. So we want to plug it into your original, or sorry, not your original, your simplified. So 1 plus 1 makes 2. So you have the point 1 comma 2. So you have a hole at 1, 2. And if there's nothing else in your denominator, then you don't have a vertical asymptote. So let's take a look if that is your vertical asymptotes, looking all over for your vertical in your denominator. Your horizontal is just a little different. Now your horizontal asymptotes, we're looking at your leading term. So you're going to compare the leading term of the numerator and denominator. Now there are three cases that could happen. One case is that of your degree. So I'll set up just what we normally have, right? P of x over q of x, again, these being polynomials, is equal to ax to the, I'll just say n, over, let's say bx to the m. And let's say these continue. I'm not going to write all of your terms, but if your degrees are the exact same, when I mean degrees, I mean n and m degree. If these are the exact same, then you have a horizontal asymptote at your leading coefficients, a over b. So there's a horizontal asymptote at the leading coefficients. That is, if your degree is the exact same above as you do below. Whereas in case 2, if your numerator is bigger than your denominator, the degree, so it's kind of top heavy. So think top heavy. So that just means there's more x values on your numerator than it is down below. Then there's no horizontal asymptote. Whereas, well, I should say even better, if the degree of the numerator is one more than the denominator, it can either have a slant or an oblique asymptote. We won't deep dive into those. I might make a separate video on your slant and oblique, but for me, we're just going to say there's no horizontal asymptote. However, it could have a slant or an oblique. Now in case 3, we have your degree of your denominator is greater than your numerator. So it's bottom heavy. So that means m is greater than n, or in this case, that was n is greater than m. Then we will have a horizontal asymptote, but this is when you have a horizontal asymptote at y is equal to 0. So those are your three cases. So you either look at if they are the same degree, it's your leading coefficients. If it's top heavy, most likely you don't have one. If the degree of the above is just one more than the degree down below, you can have a slant or an oblique. And last, if you're bottom heavy, so the degree down below is bigger than the numerator, then you do have one at y is equal to 0. So those are your three cases here. And again, we're not going to get into slant and oblique. I will make a separate video on that if you're curious as to how to find them, but we will not be really tested on that. So example 3 says, find the equation for your asymptote. So you have x plus 1. Excuse me. So if we're looking just for your horizontal asymptote, again, we're looking at the degrees of your leading terms. So if we just isolate those two, we have x squared over x squared, which we then go ahead and analyze your degree of your terms. Because they are the exact same, what kind of case do we have? Well, because they are the exact same, we're going to look at the leading coefficients. So what are your coefficients here? We have one here in front and another one. So y has to be equal to 1. Let's try it again with b. Again, we're looking at the leading terms. So we look at 3x to the 4th over x to the 6th. Make sure you check all of your terms. Sometimes we end up tucking some in just to see if you're aware and looking. So are we going to be the same top heavy or bottom heavy? Well, the degree below is higher than the degree above. So we're bottom heavy, right? That means there's more x's in the denominator. Therefore, we have a horizontal asymptote at y equals 0. So now let's take a look at the other one. So again, looking one more time. You have your degree of your first terms. You have 2 over 2x. And again, this having a bigger degree, we are bottom heavy. Meaning that we have a horizontal asymptote at y is equal to 0. Let's do it one more time. So hopefully you're pausing the video, getting a hang of these. X to the 4th over x to the 4th. So looking at your degrees, they are the exact same. So we therefore look at your leading coefficients. We have 1 over 2. So that just means y is equal to 1/2. So this is how you can pick out your horizontal asymptotes by your degrees. And again, if it's just one more than the degree above than it is below, so if it's top heavy, which none of these came out to be top heavy, it could have a slant or an oblique asymptote. Now let's take a look at common factors. So recall that when you cancel out a term from the numerator and the denominator, it results in a whole. So how do you find the whole? Well, first you're going to set your canceled factor equal to 0 and find whatever that value is, so that x value. And then you're going to find your y value by plugging it into the simplified form. So let's have you practice on this one. So find the common factors, and then we'll go ahead and graph. So down below, we definitely want to factor. And I'm hoping that you pause the video and you're just now resuming. So we factor the bottom. We factored now everything. And you'll notice that we can go ahead and cancel these out. When we've canceled, we are creating that whole. So there's a whole at x is equal to 3. So again, set x minus 3 is equal to 0. So x is equal to 3. Now to find the y value of your whole, so right now we have your x, we want to find your y. Well, the simplified graph is now 1 over x. We now need to plug in your x value to find your y value. So you can say f of 3, where your whole is, and we're going to plug it into 1 over x, your simplified form. So your whole here should be at 3 1/3. Now, do you have a horizontal asymptote? Well, we said, well, the horizontal asymptote, right? We're looking at the degree of your first term, right? The highest degree. So your horizontal asymptote. We're taking your degree, x over x squared. And are we the same top heavy or bottom heavy? Well, we are bottom heavy, right? Bottom heavy, which means we have a horizontal asymptote at y is equal to 0. So we do have one at y is equal to 0. Now, do we have a vertical asymptote we need to be aware of? Well, your vertical asymptote, I'll put this kind of right a little closer by your vertical asymptote. Or your horizontal, so sorry. I get those so wrong when I talk about them. So your asymptote of your simplified, right? We had 1 over x. We want to do your simplified because we canceled out your factors. We found a whole. So now we look at your simplified form. Now, is there a value that we still need to avoid for your x? Well, we don't want to be equal to 0 here. So we have a vertical asymptote at x is equal to 0. Now, we haven't graphed one of these quite yet, but let's give it a quick graph. We'll do something like this. If I were to quickly graph something like this, right, did we graph 1 over x already? But yeah, we graphed it over here, right? This is what it should look like. We have 1 over x. So we're going to kind of start there with the idea that that is the visual aid, right? But we have some asymptotes that we want to be aware of. We have a horizontal asymptote at y is equal to 0. We have a vertical asymptote at x is equal to 0. So these are kind of splitting your graph. So x is equal to 0. We have y is equal to 0. We also have a whole at 3 1/3. So 3 1/3. 1, 2, 3 1/3, perhaps right here, as best you can get it. That's going to be your whole. From here, if we know what the visual picture is, right, we could certainly plug in some values, which if we wanted to, we could plug in the same values as we did originally. We just would have to avoid when x is equal to 3, because there is your whole. We'll just do a quick sketch for right now, but for us, we're going to come all the way down, touch your hole. So sorry, excuse me. We're going to go to this particular point and then keep going. Let me see. I think I can draw that a little bit better. And there's a rough sketch of what your graph should be looking like. It's not perfect. We can certainly pick points if we need to, but if we're looking for a general sketch, then here we go. Now let's try and put this all together. So I'll only have you graph one of these in this particular lecture, and another worksheet we'll talk more about some of these graphic ones. So it says steps to graph the rational functions. So step 1, you want to make sure that everything is fully factored. Step 2, you could have a whole where the common factors cancel. You also have a vertical asymptote where any sort of denominators are equal to 0 after your canceled common factors. And you could have a horizontal asymptote from the leading term of your numerator and your denominator. Now, lastly, you do want to get some additional points. You want to be aware of your x-intercepts if you have them, or your y-intercepts if you have them. If you are looking for your x-intercepts, we're going to be looking at the numerator. And this would be the numerator of your simplified version. And your y-intercept, you can plug in a 0, and typically you want to do this into, again, your simplified form. So let's put it all together. So before you pause the video, I would like to make an edit. This really should be x squared minus 1. I did not get to change this edit before this video started, so my apologies. So I'd like you to pause the video now and see if you can actually use all of the skills and graph it into one problem. So you have x squared minus 1 over x squared plus 2x minus 15. So let's go ahead and factor everything to get started. We have x plus 1 and x minus 1 on top, x plus 5, and x minus 3 on the bottom. So right off the bat, do we have a hole? We have no hole, nothing has canceled. So we will not have an actual hole in your graph. However, a vertical asymptote, do we have vertical asymptotes? We should. Anything that's left over in your denominator, these will be your vertical asymptotes. So let's go ahead and take x plus 5 and set it equal to 0, and x minus 3 and set it equal to 0. So your vertical asymptotes are when x is equal to negative 5 and x is equal to 3. Now your horizontal asymptote, will we have one? Well, let's take a look at your degrees, your leading terms. So we have x squared over x squared. So are your degrees the same, top heavy or bottom heavy? Well, these being the exact same, we get to go ahead and look at your leading coefficients here. So your leading coefficients will cause a horizontal asymptote to be at y is equal to 1. Now let's go ahead and find some more special features. So let's go ahead and find your x-intercepts. Now where will this information be found? Well, this information will be found in your numerator. These are your x-intercepts if anything hasn't gotten canceled. So just like we did with your asymptotes, we're going to set them both equal to 0 to locate your x-intercepts. So we have one when x is equal to 1 and when x is equal to negative 1. So we have 1, 0. Put these over here. 1, 0. And negative 1, 0. And again, we always want to double check that, hey, like these are still valid. Perhaps you forgot that, oh, because they canceled, right, that it makes a hole, right? You can't really double dip. You can't have a horizontal or a vertical asymptote and an x-intercept. Now let's take a look at your y-intercept. Now your y-intercept, come on, one more. Your y-intercept is found when your x gets set equal to 0 in your simplified form. So for us, unfortunately, nothing has canceled. So we can go ahead and use either form to go ahead and insert a 0 for your x. So 0, 0, 0, 0 over here, 0's over here, right? And you'll be left with negative 1 over negative 15, or 1 times negative 1, which is negative 1, over 5 times negative 3, which is negative 15. So we have, oops, your vertical or your y-intercept at 1, oh sorry, at 0 and 1 over 15. Again, this is that we plug in a 0 into the equation. Now let's go ahead and graph your special features. So we have a vertical asymptote at -5. And again at 3. Keep in mind, we cannot cross your vertical asymptote. We also have a horizontal asymptote at y is equal to 1. We have your x and y intercept. So we have your x-intercept is at -1 and 1. Let's see, we have your y-intercept at 0 and 15. That's going to be right there. Maybe I make that a different color right there. So as far as your special features go, right, we have all of those mapped out. So now what we need to do is figure out, well, what does this graph look like? Right? Well, primarily, right, we have to just plug in additional values. We typically want 2 values or 1 value on either side of your asymptotes, your vertical asymptote. So your vertical asymptotes over here, we want to pick 1 or 2 points that are on the left-hand side of your asymptote. So pick a point if your asymptote is here. Pick an x value that you think you would like to plug in from the left-hand side. Let's go ahead and pick -6. So f of -6. And we can go ahead and put this either into your original or your factored. We always want to do your simplified form because it's a little bit easier to work with. However, we don't have a simplified form. We have a factored form and a non-factored. I'm perhaps going to put it into your factored form. So you have -6 plus 1, -6 minus 1 over -6 plus 5, and -6 minus 3. So that gives me -5, -7, so that's 35 over, let's see, 1, or sorry, that's a -1, and then -9, so that is a +9. So we got 35 over 9. So it's about 4, because that is a fraction that's a little hard to understand, but that's going to be about 4. So we have the point -6 and about 4. 1, 2, 3, 4. A little above 4. There we go. So when we figure out this point, if we need an additional point to plot, if we chose -7, -8, or maybe even a value that's a little bit closer, right? But your end behavior at these asymptotes, we're going to start to scrape up and then again try to approach them and scrape downwards. We want to approach your asymptotes, but they're just going to skyrocket or flatten out at these particular values. Now, when it comes to values that are in between, notice that we already have your x and your y value. And it doesn't look like it's going to be crossing at your horizontal asymptote, right? Because it looks like if we were to connect these are then going downwards. If we want to graph more, we certainly could. We could graph -4, -3, -2 to figure out, okay, well, maybe your graph does start from up here. So if we wanted to do that, we certainly could. So f of -4, -4 plus 1, -4 minus 1, -4 plus 5, -4 minus 3. So we have, let's see, -3, -5, so that's +15. We have 1, we have negative, what is that? -7. So it being a negative y value, we are looping back down here. So we can just go ahead and scrape towards these values, connect and scrape. And last one, we're going to pick a value or two to the right-hand side of your vertical asymptote. So again, we did the left-hand side of the vertical asymptote between the vertical asymptote. And now we'll do the right side of the vertical asymptote. F of, let's see, we can't choose 3, but let's choose just 4. So you have 4 plus 1, 4 minus 1, 4 plus 5, and 4 minus 3. So you have 5, 3, so that's 15. We have 9, and we have 1, so 15 over 9. So about a little more than 1.5, so a little bit more. Okay, so 4 and like about 1.6. So that's going to be up here. So somewhere up here. So again, starting to scrape up and scrape down. And that is graphing a rational function. Again, see you in your next video for some more practice on these. Again, a whole is anything that canceled. A vertical asymptote is anything that's left over in your denominator. A horizontal asymptote is anything that is present in your terms. So your leading terms here. We look at your degree, if it's top heavy, bottom heavy, or the same. Your x-intercepts come from your numerator that's been simplified. R is nothing canceled, so it's found all up above. And your y-intercept, we go ahead and plug in a 0 into your equation. We graph your special features, and then we try to plug in 1 to 2 values on the left-hand side, in between, and on the right-hand side of your vertical asymptotes. Again, you can cross your horizontal asymptotes at times, not always, depending on the graph itself. All right, and that concludes your graphing rational functions.